Hello everyone, and welcome to our first lecture this semester. In this lecture I will be covering the basic concept of chapter 1 and which section that you need to concentrate on. Before I do that, I have a couple of notes to mention. Please take the time to go back to your web campus and click on your course and watch the video that I have created for you. It's a welcome video right there. If you look in under your course, under module 0, that's what I'm saying. The first item there, video welcome to physics 151. So you click on that, and then it's a 26-minute video. It basically tells you how to navigate the course, the major items in the syllabus, and how to create an account through Mastering Physics and all that. So please take the time to watch it. That's the first note. The second note is please make it a habit before you view the video lecture of each week, each module. Please take the time to read the chapter before you do the video. I cannot cover everything that is mentioned in the chapter. It would take me probably hours of video time. So I mainly cover certain topics briefly, assuming that you have already studied it. And then the concentration, most of the bulk of the time of the video will be just working out problems from the textbook and the homework and some of the examples. So I always assume that you've already done your reading assignment. In addition to that, there will always be a PowerPoint presentation like this one here. There is like maybe 20 to 40 slides in there. I urge you to look at them, just kind of a brush up on what the chapter is all about. And then you come in as the last thing before you start working on homework. You come in and watch this video lecture, okay? That's just my opinion of how you should study for this course and hopefully succeed with a good grade. Okay, let's get on with the chapter. So the chapter is called Models, Measurements, and Vectors. The main two topics of this chapter that I want to concentrate on is unit conversions and vectors. Vectors are extremely important. Oh, and by the way, if you feel that your mathematics is inadequate, you're taking, this is maybe your first course in physics, or you've taken math a long time ago. Remember, the prerequisite for this course is algebra and trigonometry. And if you feel that you are a little bit, your math is inadequate, if you go back to the table of content, chapter 0 right here is a math review. I'm not going to be covering it in our course, nor you're not going to be tested on it. But it is optional for you. You can click there, and then you can look at those pages. It basically give you all the math that you need for the entire textbook. Okay, algebra, trigonometry. It gives you everything you need, an overview of all of that. So maybe that would be a good idea if you feel your math is not adequate. It will be a good idea for you to read that chapter. Okay, but officially we begin the chapter. Our first chapter is chapter 1. Okay. All right. Let me leave the book for a second. I want to give you the lecture on a tablet. I prefer that. So I'm gonna just make it disappear, and then I'll open up OneNote. And with my stylus pen, we're going to begin that. So, like I said, the main two topics I want to cover in this chapter are units and vectors. So units, as you all know, for those of you who have taken physics in the past, or maybe a chemistry class or something like that, you know that there are two major systems of units. One is called the SI system, and the other one is called the US customary system, or the British system. There are so many names to it. The one that we use in science is the SI system. SI stands for System International. That's a French term, or International System of Units. The US system, or the British, or it's called the British Imperial System, I think that's what it's called. It's only used in the US and maybe some few small countries, but the rest of the world uses the SI system of units. The basic measurements of units are time, length, and mass. Okay. For time, I'm going to give it the symbol big T. I'll put a T above it. And for length is big L. I'm going to put a bracket around it that means unit of time, unit of length, bracket, and then big M, unit of mass. Yes. Okay. So for the SI system, the basic unit of time is not minutes, not hours, not century. It's the second. Keep that in mind. That's the default unit. This is second. The same thing for the US system. The imperial system is also the second. Okay. For the basic unit of length in the SI system is the meter. Okay. For the imperial system, it is the foot or the feet. Okay. And the basic unit of mass in the SI system is the kilogram. And in the US system, it's not the pound, it's called the slug. Okay, probably never heard of it, but that's okay. All right, now let me just concentrate a little bit more on the SI, but this is what's important for us. The SI system, as a matter of fact, it has two subsystems. One we call MKS, the other one is called CGS, okay? MKS is basically that. M, here, with my mouse, you probably see it. MKS. See that? So MKS means meters, kilograms, second. And also there is another system, it's called CGS, where it means centimeter, gram, second. You see that? So you can choose to use, you can choose to use meters, kilogram, and second for whatever problem you're working on or whatever experiment you're doing. Or you can use centimeter, gram, second. But the issue is never ever mix the two together. In other words, never say something with a length of so-and-so centimeters and the mass of it is in kilogram. You can't do that. So if you're going to use centimeter, the mass must be in gram. Okay? If you're going to use meter, the mass must be in kilogram. If you're going to use gram, the length must be in centimeter and so on, okay? So never mix the two columns together. Who uses the CGS? Well, biologists use it, medical doctors use it, geologists, chemists. If you've taken a chemistry course, you probably remember it's always CGS, it's always gram, lots of grams there. Because that's the stuff that they use. Why they use that? Because gram, CGS rather, deals with small stuff, you know, small amount of solution. Geologists, they use a small sample of rock, very, very small, tiny thing. Biologists, the same thing. They're dealing with small objects, whatever they are, and so on. Okay, they're small samples. So a CGS would be more suitable, more fitting for them. Okay, where in physics we're dealing with a little bit bigger stuff like planets and stars, whatever, cars or billiard balls and so on. Things are colliding together, whatever. They're a little bit bigger, so it's more fitting or more suitable for us to use meter, kilogram, second. MKS, that is. Okay. So the problems in the textbook, I would say maybe 90% of them are going to be MKS. If you see CGS, you're welcome to use them, but make sure that you are using CG and S together. Never mix it with the MKS. You got that? Okay. All right. I hope that you've read the book, the chapter already. So I'm going to jump into the problems and show you how that works. And I'm going to start with example 1.1. I usually do, you know, some examples from the book if they are good. And this one, there are a couple of them they're pretty good. I'm going to use them. So example 1.1. I need to get used to this stylus pen. Okay, it says here 1.1. Should I show it to you on the book? Sure. Let me go to the book. I think I'm going to go to the what page? I'm looking at the hard copy of my book. It's on page 8. Page 2. That's what one of the things that I like about ebook. It's kind of hard to scroll. Go to page 8. Yeah, there it is. Okay. It's right here, this example. I want to do those couple of examples. It says here we will do a simple conversion of unit, although there is no maximum speed limit in the German Autobahn. This is the German highway, the interstate highway in Germany. And that's interesting that they don't have a speed limit. That's pretty cool. Signs in many areas recommended at top speed of 130 kilometer per hour. Okay, so let's assume that this is the speed limit on the particular section of the highway, 130 kilometer per hour. Now he's asking, express this speed in meters per second. Okay, so we want to know what is it in meters per second, and also miles per hour. Okay, so basically what we want to do, we want to convert kilometer per hour to meters per second and miles per hour. How do we do that? I'm not gonna, you can read his solution, but I'm gonna solve it for you. So let me, there is one thing I forgot to mention. If you go back to the table of content in the book and you scroll down to Appendix D, right here, see that? And if you click on it, you have a conversion of units there. So how everything is related. You're welcome to use it, or maybe you can just use the internet. Just go to Google and type in, let's say, how many centimeters in an inch or something like that. You can find that as well. But it's available for you. Appendix D, keep that in mind. If you manage to print it out, you can print it out and put it on the wall or something like that, so you don't need to look it up anymore. So anyway, it's right here. Okay, so let me go back to the, I'm not sure if you could go back to where I started with one click, so I have to maybe do it this way and then put an 8 there. Hopefully this will work. Yeah, it works. Okay. All right. So how do we do this problem? So it says I have the velocity speed is 130 kilometer per hour, right? Okay, let's take the latter case where I want to find it in miles per hour. I'll come back to meter per second in a second. Okay, so how do I do that in miles per hour? So what does that mean? It means that I am not going to convert the hour. The hour is still the same, but I'm going to convert the kilometer. So now I need to find a relationship between kilometer and mile. Again, if you go back to, I don't want to keep flipping between the pages, but if you go back to that Appendix D, and I have it right here in my hard copy of the book, and if I look it up, I know that there are two of them. I'm looking for which one is better. There it is. Okay, it says 1 mile is equal to 1.609 kilometer. Okay, there's another one. The second one, if you want, is 1 kilometer is equal to 0.6214 miles. Okay, whichever you want, it doesn't really matter. That's the one I memorized in my head, so I'm going to use this one. Okay, how do I do it? Okay, let me show you how you do it. What you do, you write down the unit that you are dealing with, which is right this one here. So I have 130 kilometer per hour. Now remember, I am not converting the hour. So the hour, I'm just going to leave it intact. But I'm converting the kilometer, correct? So what I'm going to do, I'm going to put a bar in here. Notice that the kilometer is in the numerator, correct? You put it now in the denominator here. There's the trick. Okay, I'm showing you a trick. You put it right in the denominator. And you are converting the kilometer into what? Into miles. You put the mile on the top. You got that? So because the kilometer is in the top of the numerator, I'm going to put it here in the denominator. If it was in the denominator, I'm going to put it in the numerator, and so on. Okay? And now I find a relationship between miles and kilometer. Well, it's one of those. Pick whichever you want. You'll get the same answer. It doesn't matter. So I'm just going to use the first one right here. So it says 1 mile. 1 mile is 1.609. And that's it. Notice that the kilometers cancel out, and I'm left with 130 right there times 1 divided by 1.609, what, miles per hour. See that? So I'm going to use my calculator. Please bring your calculator, and you can calculate things with me. And I hope you have a pencil and paper. You're writing all of that as notes. So I have 130 divided by 1.609. Answer. The answer is 80.796 miles per hour. You're done. Easy? Okay. And by the way, I'm not very big on scientific notation. I mean, be reasonable. I'm not going to punish you, or hopefully the system is not going to punish you severely for writing the wrong one. I mean, if I want to end this answer, I would probably go with 80.8 mph, miles per hour, and so on. Okay. All right. Now the second part of the problem, he said, I want to know. I'm starting with 130. To move the keyboard. I don't have a lot of space on my desk here. I have here 130 kilometers per hour, and I want to convert it into meters per second. Okay, so here I'm going to be looking for a relationship between kilometers and meters, right? And hour and second, which is kind of easy, right? I hopefully that we all know that. You can look up Appendix D or the web. We know that 1,000 meters is equal to 1 kilometer, correct? And I know that 1 hour is equal to 3,600 seconds. Okay, so I go back and I do the same thing. So just like I did here, I'm going to do the same. So I have here 130 kilometer per hour. Now, how many units I'm converting? I'm converting 2, correct? I'm converting kilometers into meters and hours into second. So in this case, I'm going to need 2 bars. Look at that. Here's 1 bar, right? And here's another one. The first bar, let's say for the kilometer. The kilometer in the top, I'm going to put it in the bottom. The hour at the bottom, I'm going to put it in the top. Got it? See the opposite? This is how you build it up. Now, I'm converting kilometer into what? Into meters. So I'm going to put the meter here. And I'm converting hours into seconds. I'm going to put a second down here. And the relationship is 3,600 seconds is 1 hour. And 1,000 meters in 1 kilometer. Done. See that? So you can go kilometer cancel out, hour cancel out. So I'm left with meters per second. You see that? So meters per second. And now I'm going to use my calculator. Go ahead and use it with me, please. And so we go 130, multiply that by 1,000, divide that by 3,600. Einstein's answer is 36.11 meters per second. And there we go. You got that, guys? Okay. The next problem is this one, and I'll be done with, well, I mean, maybe I'll do one more. There is one for my personal notes. Okay, here he says, now let's consider the problem that involved the conversion of units of time. The universe is thought to be about 13.7 billion years old, right? Part A said, what is the age of the universe in seconds? B, our species evolved about 4.7 times 10 to the 12 seconds ago. How many years is that? So basically you want to convert billion of years into second. That's the first part. And the second part, you want to convert seconds into years. Kind of a simple problem, I hope. I mean, you're dealing with big numbers, but the units are pretty simple, I hope. Okay, so how do we do it? All right, example So let me just say, it says the universe is 13.7 billion years. So part A says, what is the age in sec? Okay, so how do we do that? Well, let me write this figure down in scientific notation, maybe, or in a better way. 13.7 billion. Billion is 10 to the 9, correct? And that's years. I'm going to put it over 1. I like to put it in ratio form. And so I want to convert it into what? Into seconds, correct? So I'm going to put a bar there. And I'm going to convert years into seconds. So now the year here is on the top, the numerator. So I'm going to put it on the bottom. You see my trick? And then I'm going to convert it into seconds at the top. Then what's the relationship between them? Well, I know that 1 year is 3.14, actually 1.5 to be more accurate. 1.5 times 10 to the 7 second, okay? A quick way to remember how many years in a second, excuse me, how many seconds in a year. What's the value of pi? 3.14, right? What's the magic number in the Bible? 7, right? Something like that. The number of seconds in a year is pi times 10 to the 7, roughly, okay, which is close to this one here, as you can see. To be more accurate, it's 3.15 rather than 3.14, okay? That's just a little trick. You don't need to know it, but it's kind of a nice trick for you. So anyway, so as you can see, the years cancel out, and I have this number multiplied by this number right here, and then we calculate that. And when I do the calculation, I'm going to get 4.32 times 10 to the power of 17 seconds. That's the age of the universe. Okay. Part B, he says convert 4.7 times 10 to the 12 second. This is how long humans have been on Earth, according to the problem. 2 years. 2 years. Okay, so we do the same thing. I'm just going to write down this number. So I have here 4.7 times 10 to the 12 sec over 1, and I'm converting the sec into years. So the sec on the top, I'm going to put it to the bottom. Okay, same thing. That's year. What's the relationship between them? Well, 3.15 times 10 to the 7, and that's 1 year. Got it? So we divide. Now the sec cancel out. So I have this number right here divided by this number, and I'm going to use my calculator for that. And I get 1.49 times 10 to the 5th years. Okay. Now you can write it years. I'll put an S there. You can write it this way if you want. 149, to be more exact, 206.0 years. You know, I like this answer better. I don't know how you looked at it, but anyway, there it is. You got it? Simple. Okay, one last problem. It's kind of a little bit different, and it's related to one of the homework problems. Here it is. This is not from the book, guys. It's from my notes. We have a silicon chip has area of 1.25 inch squared. Okay, what is it in centimeter squared? You got it? So how do we do this problem? Well, now if you go to the conversion of unit appendix or the page in the book, there is no conversion of, I guess there is. I'm not sure. Here, let me look at the page. I don't see, oh yeah, there is some here. Okay, so there is a relationship between centimeter squared and inch squared. But what if you don't have it? Let's say, for example, that you know that, and I happen to memorize it as well. I know that 1 inch is equal to 2.54 centimeter. I've always memorized this ratio. Okay, but let's say I don't know what is it, the area though. Well, how do I do that? Simple. All you need to do is to square both sides. See what I'm saying? In other words, it's 1 inch squared also must equal to 2.54 centimeter quantity squared. If you want it in cube both sides and so on. So when I square both sides, I'm going to get 1 inch squared is equal to now 2.54 squared. I need to look up my calculator. 2.54 squared answer. It is 6.452 centimeters squared. There we go. I have a conversion factor between inch squared and centimeter squared. I didn't need to look it up. You know what I mean? Now, if I look it up on the book, I have it right here in front of me. Area, he says, he gives me this one. If I'm not going to depend, he said 1 centimeter squared is equal to 0.155 inch squared. And I bet you it's the same as that, except I just reversed. But anyway, I'm just going to stick with the way I did it, okay? So there we go. I have that. Now let's go back to the problem. He said I have a silicon chip. Let's assume it's square, you know, so whatever shape of it. Let's say it's a rectangular or square, whatever. And he said the area of this thing is 1.25 inch squared. Well, what is it in centimeters squared? Okay. So how do I do that? Well, again, I'm just going to write it down. 1.25 inch squared over 1. I'm going to put that big long bar, and the inch squared on the top, I'm going to put it on the bottom, right? And this is going to be the centimeter squared, and then I'm going to write down the relationship between them. Now you can use this one, the one I looked up on the book, or the one we came up with. Okay, I'm going to use the one we came up with, this one. Again, it doesn't matter. You'll get the same answer. So we have here 1 inch squared is equal to 6.452 centimeters squared. Of course, you can slash the inches squared like that, or in your mind's eye, you know they're going to cancel out, and you're going to be left with only centimeter squared. So I'm going to use my calculator now. So you go 1.25 times 6.452 answer, and the answer is 8.06 centimeter squared. There we go. That's the area. You got it, guys? Okay. And that's the end of the first part. And like I said, I want to talk about 2 parts in this chapter, and that is units and unit conversions, and also I want to talk about vector. This is the big subject, so pay attention. And that's the last topic. What is the big topic? Vectors. Again, I cannot talk about everything about vectors, so please take the time to read from the book. I'm going to cover it, and then we'll do some problems, and some of the homework problems as well. Okay, so what is a vector? A vector is a quantity that has magnitude and direction. A lot of you, I'm sure, know that. For those of you who have taken previous course in physics, you have a magnitude and direction. What does that mean? When I say something, it gives you a sense of direction. For example, let's say you're going to the mall, okay, and you are about to open the door of the mall, Macy's, for example, and you see a sign on the door that says push. Now you know exactly what direction to do. You're going to push it forward, away from your body. If it says pull, you know what to do. If it says lift or whatever. So there are certain words that you read, immediately it gives you a sense of direction, like the word push, lift, and pull. You know what I mean? Same thing in mathematics or physics. We have certain quantities that immediately give you a sense of direction, or it begs for a direction. One of them is velocity versus speed. We'll talk about all of that later. But for example, what is speed? Speed is basically, you look at, when you're driving your car and you look at the speedometer and it says that you are going 35 miles an hour. That's it. That's speed. It doesn't tell you you're going 35 miles an hour to the north or to the west or upward, whatever. It doesn't tell you anything. It just tells you the speed. So you could be going any direction and it's just going to give you that number, but it doesn't give you the direction. If there is no direction, then we call that speed. That's 35, this number, we just call it speed. But if it says something like you are going 35 miles an hour north, that's velocity. Okay? So velocity is a number and direction, okay? Where the speed is only a number, 35 miles an hour. This number is what we refer to as the magnitude, this fancy word, okay? So when we say 35 miles an hour north, well, here, 35 miles per hour north, this is direction. And this word right here, this number, excuse me, is the magnitude. So the speed is this number only. But when you add direction to it, immediately it becomes a velocity. Got it? Okay, so velocity is a vector. Why? Because vectors have magnitude and direction. Another example of vector, force. Just like the word push and pull and lift when you go to the mall, push the door or pull the door. That's a force. You have to apply a force. Well, what direction? I mean, I'm going to apply a force. I'm ready to apply a force on the door to open it. Well, what direction? Should I pull it or push it? It tells you push. So the push, you know what direction is it. So you go here, you apply the force, let's say you apply a force of 3 pounds, for example. The pound is a force, in the direction of the push. You can do that, which is away from your body. Or you can say 3 pounds north or south or to the right or upward. All of these give you a sense of direction. It doesn't matter how you do it. Okay? Or the one we use here in physics is, let's say 3 pounds in the direction of 30 degrees WRT X direction. 30 degrees with respect to the x-axis, let's say. That's also a direction. You see what I'm saying? There's so many ways to describe direction. It could be, like I said, it could be north, south, geographic direction. It could be right and left in terms of your hand. It could be up and down. It could be, the most accurate of all, in my opinion, is the angle. You give it an angle with respect to the x-axis or the y-axis or whatever. This is more accurate, especially if you want to do calculations. Okay? So all of these are directions, and then that amount, the magnitude, the quantity that you're dealing with, 3 pounds or 3 ton or whatever, okay? That's what we call the magnitude, okay? Another vector quantity is acceleration. Again, we'll talk about acceleration next chapter. It is the act of speeding up. I'll come back to it later. And there are others. I mean, there are many others. Now, and the opposite of a vector, we call it a scalar. What is my vector here? Did I write the word vector? Oh, there it is. So the opposite of a vector is what we call a scalar. So what is a scalar? A scalar is something with just a magnitude. That's it. No direction. Okay. For example, the speed. What your speedometer is reading while you're driving a car. You could be driving north and south and whatever. It's just going to say 35 or 25 or whatever. That's a scalar quantity. Okay. Another one. Your temperature. When I measure your temperature and it is 98.7, okay? Does it give you a sense of direction? No, it's just the quantity. It's a scalar value. How old are you? I'm 22. Does it give you a sense of direction? No, it's a scalar value. Your height, For example, how tall are you? Or what's the length of your arm, for example? It's all scalar. They don't give you a sense of direction, okay? So these are scalar values. Okay, and we symbolize, let me go back to vector. This is our subject. We symbolize the vector with an arrow. It looks something like that. Don't put a tail on it like that. We don't want to do the tails. Whoops. Just like that. We call this part of the arrow the tip. Okay? And we call this part of the arrow the tail. Okay? So tip and tail. Got it? And the length of the arrow, or we call it vector, the length of the vector is the magnitude. Got it? And the direction is basically, well, here is the vector, here is the x-axis, let's say. This is the angle theta with respect to the x-axis. This thing is what we call the direction. Just like I told you here on the previous page. Remember that? Right here. It's at 30 degrees with respect to the x-axis. WRT is kind of a cool abbreviation. Remember it. I use it a lot. I like to use it. 30 degrees WRT with respect to the x-axis. 30 degrees. That's basically direction. So the direction, we refer to direction in terms of an angle. And so I'll give an example. Let's say I have a vector. I'm going to call it F. And we symbolize the vector with an arrow on top of the letter. Okay? In your book, you'll find it in bold. I believe it's in bold. Let me go back. Some books, they don't have it in bold. Let me look at the hard copy, then I'll show you the actual one. Sorry, yeah. Let me go back to the book. Look at that. For example, page 12. Oh yeah, there is an arrow. I'm sorry, there it is. See that? See the arrow right there? Let me make it bigger. Come on. There we go. There we go. See the arrow? The arrow here is a vector. Okay, in some books, actually two things. An arrow and it's written in bold. Do you see that? If it's bold and an arrow on top of it. See, these are all vectors. You get that? Okay. So if I have a vector, I forgot what I was talking about. I have a vector F. I honestly forgot what I was talking about. Why do I want to say that? Anyway, anyway, so we symbolize the vector with an F, a letter A, B, C, D, F, whatever letter you want, with an arrow on top of it. And of course, the magnitude of the vector, which means how tall it is. Oh, I know what I want to talk. Let's assume that this vector is, let's say, 2 pounds. Okay? Let's assume that. That makes it what? That's the magnitude of it, right? And the direction, let's say angle is 30 degrees. So how do I do that? Well, I need to determine whether it's 2 pounds. Let's just say 2 pounds, it means 2 inches. In other words, 1 pound is 1 inch. Remember I told you the length of the vector? Here. Remember I told you the length of the vector, told you about the magnitude of it? So let's say that 2 pounds, 1 pound symbolizes 1 inch. So if I'm going to go and so here's my x and y axis. And assume the vector is 2 pounds. So that's 1 inch right here and another inch right there. So that's my vector F. That's 2 pounds. And that's the direction, 30 degrees with respect to the x-axis. You got it? Now let's assume I have another vector. I'm going to call it, let me call it P. Okay? And it is 4 pounds. And it is theta equal 45 degrees. And I'm going to draw it on the same coordinate system here. Okay? So how do I do that? Well, here. Let me take this 2 pounds and just write it maybe here. And so I'm going to draw, this is not really, this 30 is a little bit, it's not 30 really, it's almost like 30, 45. But anyway, let's assume it's 30. So here is a 45. It's not drawn to scale, sorry about that. But it's going to be, this time it's going to be 4 pounds. What does that mean? It means it's going to be double the length of this vector. You know what? I'm going to draw it all over. This is not drawn to scale. It's kind of clumsy work. Let me do here is the 2 pounds, 30 degrees. Let's assume it's this one right here. Okay, so this is the force. That's 2 pounds. And that's, let's say this is 30 degrees. The 45 is going to be what? It is 4 pounds, which is double the 2. So it's going to be double the length. I'll try to make it as much as I can. Here is about 2 here. Here's another 2. So it's roughly there. And you see what I'm saying, guys? And the angle here is 45 degrees. You got it? So here the magnitude, let's say, I'll talk about the P vector. The magnitude here, mag, is equal to 4 pounds. And the direction, let's call it dir, theta equals 45 degrees. And that's what makes it a vector. Magnitude and direction. Okay? Good. Okay, let's do some math now. Okay, now I want to represent it mathematically, or at least graphically for now. So let's say you always start with a Cartesian system, x and y axis, like that. And let's say I have a vector like this, okay? I'm going to call it vector A. Okay, don't forget to put an arrow on top of it. There is an angle here. This is the x-axis. This is the y-axis. Every vector in the Cartesian plane, in the two-dimensional Cartesian plane, we're not going to be studying three-dimension, that's a little bit more advanced mathematics. But in the two-dimensional Cartesian plane, it has 2 components. One component is called the x component, and the other one is the y component. This length from here to here is, we call that a sub y. The y component of the a vector. Got that? And the here, from here to here, is the a sub x, the x component. And as you know from trigonometry, if you remember, if I have a triangle, let me just do it on the side here. There we go. This is the opposite, if you remember. This is the adjacent, and that's the hypotenuse. So we say that, what do we say? Sine theta is equal to opposite over hypotenuse. Oops. And cosine theta is adjacent over hypotenuse. I'm not doing the y correctly. And then we have tangent theta is equal to opposite over adjacent, correct? And with these in mind, I'm sure you know all of them. I know high school kids, they have a word for it, sakutoya or something like that. I hear it from high school kids. There's some word that they use to memorize them. Anyway, however you memorize them. So in this case, looking at our diagram here, I can find that a sub x is equal to a cosine theta. Okay, I can put the arrow there, but it's not necessary for this matter. If I'm just looking at it as a triangle. And then a sub y is equal to a sine theta, correct? So make sure you remember that. I would urge you actually to just memorize it for, once and for all. Ax is always a cosine theta, and ay a sine theta, provided that, this is very important, provided that the angle theta is measured with respect to the x-axis. If it's with respect to the y-axis here, then the reverse is correct. You know what I mean? So whenever you see a vector and you want to use those 2 formulas right there, always make sure that the angle is measured from the x-axis, not from the y-axis. You got that? Otherwise, if it's on the y-axis, the a sub x becomes a sine whatever that angle on the y-axis. Okay? But for the x-axis, with respect to the x-axis, it's a cosine. With respect to the y-axis, it's a sine. Got it? Okay. What does that mean? Well, let's say, for example, let me just give you a simple example before we do a heavy problem. Let's say I have here's my Cartesian plane. Let's say I have a vector A, and let's say it's 5, whatever it is, 5 pounds or 5 meters per second, whatever it is. And let's say the angle here is 30. Okay. So a sub x in this case is going to be what? Again, look at those formulas right there. So that's just going to be 5 cosine 30. and that's equal to 5. Multiply this by cosine 30 is what? 0.866, or square root of, your math teacher told you square root of 3 over 2. I memorize it as 0.866. You just use your calculator, you're going to get that. So I'm going to use my calculator right now. So 5 times 0.866, answer 4.33. Let's assume, for the sake of argument, this is pound. Okay, let's say it's a force and it's pushing on something here, whatever it is. Okay, a table. So that will be 4.33 pounds. A sub y is 5 sine 30. I've always memorized sine 30 is half, so that's just half times 5, and that will be 2.5 pounds. And there we go. Okay. Now here is something interesting. If I use the Pythagorean, remember that if you go back to the triangle here, this triangle here, let me redraw it again. Here it is. Here's the angle theta, and this is the hypotenuse, right? Let me call that y, and we call that x. As you know, x squared plus y squared will give me the hypotenuse squared, right? So in this case, the hypotenuse squared, excuse me, the hypotenuse rather, is equal to the square root of x squared plus y squared. We can check it here with our, what we have in here. Let me redraw that in terms of components. I have basically a triangle. This is the A, which is equal to 5, and this is the A sub y, correct? And that's 2.5, and that's A sub x right here, and that's equal to 4.33. If I would use the Pythagorean, this formula right there, in other words, 4.33 quantity squared plus 2.5 quantity squared, all of that under the root. Go ahead and use your calculator. I bet you're going to get 5. Okay? You're going to get the hypotenuse there. Okay? You do the calculations. So this is important. Keep that in mind. All right. Here's an example. This is, again, from my own notes. And this is very, very important example. There are 2 problems from the homework that are directly related to it. So make sure you understand it. Let me draw the picture first. So that's an example. Again, this is from my notes, not from the book. I have a Cartesian plane right there. And I have 2 vectors. Here's one. I'm going to call that vector A, and it's equal to 6. Maybe 6 pounds, okay? Whatever it is, 6 pounds or whatever. And I have another vector. It's going like that. A little bit shorter. I'm going to call it vector B, and it's equal to 4. Okay? Let's assume that the angle here is 30 degrees. Keep things simple. And let's assume the angle here 45 degrees. Okay? And I want to know the resultant vector. Resultant vector. What does that mean? What's the meaning of the resultant vector? Okay, let me tell you. Let's assume that this picture that you're looking at here, okay? Let's assume, right at the origin of the coordinate, right there, okay? Let's assume there is something there. Let's assume there is a table. Let me draw a picture. Let's say here's a table, okay? And there are 2 people who are pushing on the table. There is a nail here, and the nail come out of the nail, let's say 2 ropes. 1 rope this way and 1 rope this way. This rope is B. This rope is A, okay? Or those 2 guys, 2 people. One is A, one is B. Got it? And those guys are pushing the table in that direction. Now the question is, which direction the table is going to move? Okay? See the question? Let me repeat it again. Which direction, as a result of those 2, which direction? It's not going to move in the direction of A, and it's not going to move in the direction of B. It's going to move in the direction somewhere in between them, correct? Well, I want to know exactly what direction somewhere between them. That's the point. That's the question. And that's what is called the resultant vector. So the resultant vector is that given a bunch of vectors, given a bunch of forces, let's say you have 5 people fighting over a loaf of bread. Here's a loaf of bread. It's a silly example, but you get the idea. Here's a loaf of bread. And you got 5 people fighting over it. Everyone is pushing it in a different direction. Let's go like this. Hold on. Let's say this, okay? So there are 5 people pushing it. The strongest, of course, is this one. See, but why do I know this is strongest? Because it's the tallest vector, the longest vector. This is the weakest right there. See what I'm saying? And this one a little bit longer or stronger than this one, and so on. You got the idea, right? So if I put a Cartesian plane on that, an imaginary Cartesian plane, like that, so I can say that this we'll call them ABC, A, B, C, D, E. So A is pushing with an angle of 30 degrees with respect to the x-axis. This guy is pushing with a 20 degrees with respect to the y-axis. Again, I'm guessing numbers, okay? And then this one, let's say also 20, and this guy is only 10 with respect to the y-axis, and so on, okay? Oh, I forgot about this one. And this one, let's say 45 degrees, okay? So as a result of all these people pushing, everyone is pulling, fighting over that loaf of bread or whatever it is. Well, which direction this loaf of bread is going to move? I'm assuming it's not going to break. Well, which direction? Well, God knows. I don't know. But there is a way to calculate it accurately, which direction. Let's assume that as a result of all these forces, the loaf of bread is going to move, let's assume, in this direction. This way, for example, I'm guessing, okay? This is what we call the resultant vector R. And then you want to measure the angle of that resultant vector. We call it phi, the direction. Do you see the plan? Everybody understand that? So the resultant vector is given a bunch of vectors on something. As a result of all of them together, combined together, there will be one vector that is a result of all of them. Okay? So I want to show you a way. How do you find the resultant vector? This is extremely important. We're going to be using this technique all through the semester, finding resultant vectors. Okay? And I'm going to give you a recipe on how to do that. Here is how you do it. Let's assume, okay, before I do the problem above, I'm going to do this problem in a minute, okay? This problem right here. I'm going to do it in a minute, but let me just give you the recipe first. Please write it down and kind of take notes of it. So let me draw another. Let's say 2 vectors, one here and one there, similar to ours. Call this B, make this a little bit bigger. And I have this angle, call it theta. Let's call this angle alpha, okay? And I want to find the resultant vector. First thing you do, resolve, this is step number 1. Resolve all vectors into components. Let me just write it down first and then we'll apply it. 2. Get R sub x, which is the x component of the resultant vector. Okay? How do I find that? Well, it's simply a sub x plus b sub x. I have 2 vectors here, a and b. If there is c, let's say there is another vector here. Let's make another one. Let's say there is another one like that. Here is c. Okay, with some angle beta. So plus c sub x, okay? And then get r sub y, which is a sub y, plus b sub y, plus c sub y. Got it? That's the second step. Third step. Use the Pythagorean to find r, the magnitude. How? This. R sub x squared plus r sub y squared. You'll get the magnitude. Remember what we said about the word magnitude, the number. And the last step for get the direction. So this is magnitude, get the direction. How do I do that? Simple. Phi equals tan inverse r sub y over r sub x. Memorize it. There we go. This is how you find the direction, okay? That's basically the recipe. It's a simple recipe. So let's apply this to the problem that we have just done. I hope you've written all of that because it's going to disappear from the page, from the screen. And I want to do this problem right here. Now, the stylus pen is not helping. It's not moving for some reason. Oh, I know. It's there. There we go. I want to solve this problem right here, guys. Okay. So let's go back. Again, I hope you've written the recipe. Let me draw it again very quickly. So I have this like that. I have the vector b. It's 45 with respect to the y-axis. Yes, with respect to the y-axis, right? And then I have another one here, a equals, I think 6. Is this 6? 6, yes. The other one is 4. Okay. Oops. To move the screen, I'm actually put my hand on the screen and move it with my fingers. Anyway, this is 4, and that's 30. Okay. So now I'm going to use the recipe. First step, what does it say? Resolve all vectors into components. Well, before I do that, I played a trick with you. Remember I told you all angles must be written with respect to the x-axis. So what I'm going to do, I'm going to get this angle right here, not this one, because this is written in respect to the y-axis. So I can ignore this angle right here, and I'm going to use this angle, which happens to be the same. So that's the angle I'm going to be using, okay? So let me get a sub x. Remember, a sub x is what? A cosine 30. Cosine 30 is 0.866 times a is 6. So 6 times 0.866 equals to, use my calculator, use yours please, 0.866, answer 5.2. There we go. A sub y is a sine 30, so that will be 6 times half, that will be 3, is that right? And then b sub x, now watch out, b sub x is right here, guys, see that? So that's the negative part of the x-axis. You want to be really careful. You got to put that minus sign in there. So that's going to be b cosine 45. Cosine 45 is 0.707. So that's 4 times 0.707. Now use my calculator to get that number. 0.707 times 4, answer 2.83. 2.8. So just say 2.8. Keep it simple. And then b sub y, which is right here, right? So b sub y is b sine 45, and we're going to get the same answer, right? 2.8. And there we go. I got all the components. See? I got all the constituent components. That's the first part of the recipe. It says resolve all vectors into components. There they are. I got them all. Now the next step is I want to find r sub x and r sub y. Simply add up the x component to get r sub x, add up the y component to get r sub y. Okay? Let's do it. So r sub x is nothing but a sub x plus b sub x. The answer would be 5.2. 5.2 plus b sub x. Oops, I forgot to put the minus sign here, right? So I'm going to put a minus sign there, a minus sign there. I bet you're screaming at me. There we go. So that's going to be minus 2.8. So now, use my calculator, 5.2 minus 2.8, answer 2.4. So I have 2.4 for r sub y, r sub x. R sub y is a sub y plus b sub y, and that will be a sub y is 3 plus 2.8, and that will be 5.8. And there we go. I got r sub x and r sub y. Okay. Next step. Use the Pythagorean to find the magnitude. How do I do that? Well, r sub x squared plus r sub y squared under the root. Do that. So r, let me just write the word magnitude here. So r is basically 2.4 squared, this is r sub x right there, plus 5.8 squared, and then I'm going to calculate that. I'm going to hold on a minute. I want to make sure. I'm looking at my notes. Is that a problem that I'm doing? Hold on. I did this problem in my notes, and I'm not getting the same answers. Hold on. Just give me a second. Sorry. I'm just looking. I want to make sure. If I was in class, somebody would have raised their hand and say, "Hey, you're making a mistake somewhere." Let's see. I want to make sure I got the same number. So I got this one correct. 3 is correct here. Negative 2.83 is correct, and then 2.8, I think I'm doing it right. R sub x, I got R sub x to be 2.37. Oh, okay, okay, I had more significant figures. Let's just assume this is 2.4, it's all right. And then this one is 5.83, okay, minus 5. That's fine. I think we are doing all right. Okay, so let me calculate this, guys. So let's do that. Let's calculate together. So when I do that, I have... I'm going to use my calculator, and you go ahead and use yours while I work on mine. Squared plus 5.8 squared, and answer 6.27. Anybody got that? 6.28 rather. Okay, so let's just assume it is 6.28. And there we go. I got the magnitude of it. In other words, as a result of these two vectors, the magnitude, here is the tip-to-tail method. I hope you studied from the book. The vector that we're looking for, let me give a, here's the resultant vector r, but we don't know that yet. I'm kind of showing you ahead of time. But that's how it looks like right there. So anyway, so we have this. Here is the resultant vector. Let me go back to black color. Okay, and then step number 4 is basically, now it's thinner. I'm sorry. Okay, so we have here phi, which is the direction, right? Go back to this here. It says the direction phi is right there, is tan inverse of ry over r, the ratio of ry and rx. So that will be tan inverse ry over rx, and that will have tan inverse ry. I already got it. Ry is 5.8, correct? Divided by x is 2.4, and then I will use my calculator to find that angle. And by the way, that angle will automatically be with respect to the x-axis, not the y-axis. So you can rest assured this is with respect to the x-axis. So I'm going to use my calculator. Tan inverse 5.8 divided by 2.4. Answer 67.5. So the angle here is 67.5 degrees. And there we go, I got the angle. In other words, if I go back to the picture here, this is the r vector right there. Okay? The angle phi, which is this one right here, that angle phi is equal to 67.5. 0.5, yeah, 0.5 degrees. And there we go. You got it? Okay, good. Now, I am done talking about vectors, so let me do maybe a problem or two from the book. So let me go to the book, and I want to do these are homework problems. I'm going to do number 36 and 49. I'll let you do the rest. Honestly, the rest are not bad. I mean, if any of them is bad, you're welcome to ask me, post your question, and I'll be more than happy to help you. But I'm going to do number 36 and 49. So let me go to the problems. Again, I showed you the trick in the welcome page. How do you go to the problems? You go with chapter 2, and then you go backwards rather than scrolling through, unless you know the page number. So number 36, one more. Right there, see the problem right here? Shall I magnify it? Yeah, let's go this one. Right here, guys, you see it? Okay. So let's read it together. It says a rocket fires two engines simultaneously. One produces a thrust of 725 Newton. Newton is a measure of force, just like pound, but it's in the SI system. We're going to study Newton's law later. Anyway, so that's just a force, just a unit of force. So one produces a thrust force of 725 Newton directly forward, while the other gives a 513 Newton thrust at 32.4 degrees above the forward direction. Okay, I'm going to draw a picture for you right now. It says find the magnitude and direction of the resultant force, the resultant vector of these engines exert on the rocket. Okay, so let me show you a picture how it looks like. Always draw a picture, always. I mean, it will help you solve the problem, what is called a free body diagram. Always draw a picture to look at it. So let's see how that works. I think I fixed the thickness of the pen already. Yes, I did. Okay. Okay, so what it says, let's read the first part of the problem. It says one produces a thrust of 725 directly forward. Well, what is forward? Who knows what forward? It could be up, down, whatever. So I'm going to assume it's along the x-axis, okay? I mean, you're free to pick whichever direction you want. So along the x-axis means forward. While the other, this is the force at 32.4 degree above the forward direction. So the picture will look something like this. So here is my Cartesian plane. And we're going to assume this is the forward direction, okay? So the first one is, here is the first force. I'm going to draw a long one just like that. Again, this is just a free body diagram, nothing precise. So that's 725 Newton. I'm going to call it F1. You want to call it whatever you want, but I like to give it a name to it. So F1. The other one, he says, it is 513 at an angle of 32.4 above the forward direction. What does that mean? Well, here is the above. So it's a little bit shorter, just like that. I'm going to call that F2, and it is 513 Newton at an angle of what? 32.4 degrees. So what he's asking for is what is the resultant vector, okay? So we're basically going to follow the recipe. You see what I'm saying? So again, this is the y-axis, this is the x-axis, and the x-axis is the forward direction. You could have chosen y to be the forward direction. It doesn't matter. You would get the same answer. Okay, so how do I do it? Well, let's follow the recipe. Remember the recipe? Step number 1, find the x and y component. Well, what is step number 1? Oops, sorry. Find x and y component. So f1x is equal to what? Well, look at that. The vector f1 is already on the x-axis. So the x direction is really the whole vector. Make sense? So it's going to be 725. Now f1y is 0, right? Because there is no component. There is no angle. So it's just going to be 0. Make sense? F2x. Well, what is it? F2x. It's just going to be F2 cosine theta, which is 32.4. You agree with that, guys? Go back to the recipe. It's the same thing. I'm not doing anything different. That's going to be 513 times cosine 32.4. Go back to my calculator. Cosine 32.4. Answer 0.844. Now you multiply this whole thing times 513. Answer 433. 0.14 Newton. Okay? And then F2x, well, what is it? F2 sine 32.4. Again, I can do this in one shot. So sine 32.4, multiply this by 513. Answer 274.9. 274.9 Newton. There we go. That's my first step in the recipe on how to find it. Second, let me find R sub x, the resultant vector, the resultant force, or rather the x component of the resultant force. So R sub x is just going to be what? F1x plus F2x. So that's going to be 725 plus 433.14. And when I do that, 725 plus 433.14, 1158.14 Newton. Okay? And then R sub y is F1y plus F2y. Well, F1y is 0 right there. F2y, I just found it above there, 274.9. So that's just 274.9 Newton. Okay? Step number 3, what is it? I want to find the magnitude, R, which is the Pythagorean. 1158.14 squared plus 274.9 squared. And then I'm going to use my calculator again. Go ahead and use yours. So that's going to be answer. I hope I did it correctly. It's going to be 1190.28. 1190.28. I hope it is correct. There we go. And the last step, so this is the magnitude, right? Mag. And then the direction. So it's phi, remember? Tan inverse of R sub y over R sub x. So that will be tan inverse of R sub y is 274.9 divided by 1158.14. And if I calculate that, I get 13.4 degrees. So there we go. So I have the vector R is equal to 1190.28 Newton, hopefully it's correct, with direction 13.4 degree, 13.4 degree WRT x-axis, or forward direction, with respect to the forward direction. And there we go. You got it, guys? Simple? Okay. The last problem that I want to do for this lecture is number 49. Let me go back. Oh, I have the book here. 49. 49 right there. Right there, guys. See it? Okay. It's level 2. It says velocity vector A has component a sub x3 and a sub y4. Okay. A second velocity vector B has a magnitude that is twice that of A. Magnitude. Twice that of A, and is pointed down the negative x direction. Okay? Find A, the components of B, and B, the components of A minus B. Okay? It's not like a hard problem, but it's not bad. It's more of a math problem, really. Okay, how do we do this one? First thing, I need to draw a picture. Remember I told you, always draw pictures. It will really help your brain think about it. So always draw a picture to aid your imagination. And then, try tackling it from there. So let me read it again. I want to make sure I understand it. He says the velocity vector A has a component 3 and 4. Okay. Let me swap between them. I don't know if I can put that on the side and it's still shown on the screen. Right there. Maybe like that. I'll come back to it. Number 49. You know what would be a better idea for you? When next time you watch my my video, just have your book open already so you can look at it without you waiting for me to show you the book. I think that would be an easier, simpler one. Anyway, so what we have, he says you have a vector A, and the component of this A sub x, is equal to 3 meters per second, and the component A sub y is equal to 4 meters per second. I'm actually reading it from the hard copy. And then he says, now listen to what he says here. He says, we have a second vector, B. The magnitude, okay, the magnitude of that B is twice that of A. In other words, B here is equal to 2A. This is important. I'll come back to it. Okay? In other words, what does that mean? Remember, this is magnitude. First of all, what is the magnitude of A? Well, A is Pythagorean. A sub x squared plus A sub y squared, correct? So I have here A sub x is 3 squared plus 4 squared. That's basically a 3, 4, 5 triangle. So A is 5. There we go, right? So A is 5. Yes? But he said B is twice A. Aha. So therefore, B is 10, correct? Or rather, 2 times 5. That makes it 10. So I know something about B now. The magnitude of B is 10. Got it? So let me box it here. Okay. Next. So let me repeat what we've read here. It said the vector A has a component 3 and 4. I have a second vector B. The magnitude is twice that of A. Well, I got it. Here it is. B is equal to 10. Okay. The first part is find the component of B. Now I need to find the component of B. But there is something else he mentioned. He says B has a twice the magnitude of A, and look at this, and it is, can I highlight that? Yeah, and it is pointed down the negative x-axis. Now this is very important information. If he doesn't mention that, I have no idea how to find the component of B. Okay, but this is the lifesaver right there. What does that mean? Let me draw a picture. Here is my Cartesian system. First thing, I'm going to draw A. He says A sub x, nope, yeah, A sub x, he said A sub x is equal to 3 and A sub y is equal to 4. So I can draw that. Well, here is the Cartesian system, x and y. A sub x, so 1, 2, 3. This A sub x right there, this one. And A sub y is 1, 2, 3, 4, right? Well, here is the vector A right there. See that? That's the vector A. It is equal to 5 magnitude. The length of it is 5. This is 3. This is 4. He said B is twice the magnitude, means twice the length, and it is what? It is along, pointed down the negative x-axis. So it's like this. So if this is A, guys, from here to here, it's twice that. About from here, another one, maybe around there, let's say, okay? So here it is. It's along the x-axis. Here is the vector. It's sitting right there, laying on the y-axis, on the x-axis, and it's equal to 10. So what is A sub y? Immediately is what? A sub y. I'm sorry, B sub y. 0, right? There is no B component. That's what he says. And what is B sub x? 10? No, negative 10, correct? Why negative 10? Because it's on the negative x-axis, he said. Here, the negative x-axis. And there we go. So now let me go back. I think I'm done with the problem. He says, find the component of the B. Well, there they are. There they are right here. I found them. And that's part A. And part B, he says, find the component of A minus B. Okay, so we want A minus B. A minus B. Well, how do I find that? Well, one way to do it is in terms of component. A minus B as vector, it means A sub x minus B sub x, and find A sub y minus B sub y. Well, what is A sub x minus B sub x? That means 3 minus 10, correct? And that's equal to 13. And A sub y minus B sub y, that's 4 minus 0, and that's 0. So therefore, the vector A vector minus B vector is, I can't actually draw it. Sorry, it requires some advanced mathematics. There's no need for that. And I think that should be sufficient. So it's those are the two vectors here, the two components of it. Did he say component or the vector here? Find the component, yes, find the component. So there they are. These are the component. The x component of A minus B is 13, and the y component of A minus B is equal to 4. And that basically should be good enough. But as you can see here, I was able to solve this problem, or what helped me immensely is drawing a picture. Okay, had I not drawn a picture, the problem would have been a little bit harder. Okay, so make sure they always draw a picture to aid you in solving problems like this. And I think I am done with what I wanted to talk about. Please let me know if you have any questions regarding homework or anything else. If you must write me an email, that's fine. Just please be very brief about your description, what you want to write. And I prefer if you just, post your question under Ask the Professor. And that's it. Have a wonderful day. Bye.